Okay, in this demo, we're going to go over a Wi-Fi workflow for an adaptive antenna selection design. So this is going to be an autonomous cloud-on-cloud workflow, and then you can see it will just give it the instructions, and then it will just run this entire thing autonomously based off a skill that we have built. So we're going to do this entire workflow based off parametric antennas, but this can equally be done with HFSS designed antennas that you want to test for yourself. This is just for demonstration for demonstration purposes. So what we're going to do is first import an indoor office environment. So this is using SBR Plus, and then we're going to assign materials to them. So you can kind of see the structure. There's a bit of a hallway, and then there's a bunch of offices. And then when it does a little bit of the coloring, I think it will become more obvious. So you can see the glass windows, the walls, the doors, the desks, the stairs, and yes, and it's just assigning materials, as you can see, and just building everything up. And now what we're going to do for this specific demo is for the antennas. We're right now, I'm just going to pause. I'm going to narrate over this. This is a playback video, so I can narrate over it, but we're going to put 8 directional parametric antennas in a ring to represent the access point. And what we're going to do is we're going to switch them on and off in post-processing to find the best selection for a specific receiver. So right now, yes, you can see it's just putting the different like antennas on. So 4, 5, 6, just placing them in the entire thing. And what we're going to compare this to is an omnidirectional antenna. So at the same point that you have this access point with this ring of directional antennas, you're going to also have a test where you do it with just one omnidirectional antenna as your access point. And I'm going to place 3 different users in this environment in different rooms at different, obviously, distances from this access point. Now, I've already solved this project in a different file or different AEDT project, and then I'm just going to reference. I just wanted to show you how the build looks, but I'm gonna do the solve based off the solved thing that we have in the adaptive array office, just to save some time for demonstration purposes. And you can see on the right hand side this entire thing, I'm not touching anything. It's a cloud on cloud workflow and just all happening autonomously based off a skill. So ideally you put your own HFSS antennas with your own designs, including your matching networks and everything, and you can run this entire skill the same way that it's getting ran right now. Just loading. You can see these little blobs where my users are. I'm going to pause the video here. You can see this green blob right here. This is going to be user 1. This yellow blob in a different office, that's going to be user 2, and this red blob, which is user 3, in a further office, just to show different conditions and shadowing effects. And yeah, so yeah, just to show you what's going on. And now so what has happened is it has performed like this. It's already been saved, but this is a near field solve or setup that it's done, and it computes the field at each of the grid points. So on the right hand side, it will just explain everything that's going on. I encourage you to pause the video so you can just read it properly, but I think it's better I do the voiceover when our final plots go up, and I can just explain everything a little bit more illustratively than just reading this over. But I encourage you to stop, pause it, and just take a look when you get a chance. But this is, again, like, this is all autonomous. Nobody's doing anything, and it's just running on the side, just commanded by this thing. So I'm going to take a moment to pause the video here. So when I was talking about this near field setup, what is happening is, first, for the omnidirectional antenna, it's going to just we're going to compute the field at a set of grid points. So at z equals 1, and everywhere in this entire, we're going to sample the field and just compute it everywhere. And then assuming we have a dipole, we're just going to compute the received power based off that. So you can see this little, let me just continue it a little bit so maybe it's a little bit more illustrative. So I'm just gonna move it around so you can see it a little bit better. But yeah, so basically this is the setup that you have. So this little box, this hallway, is exactly where this is. This is where your access point is, user 1, user 2, user 3, just like there that you have them. and you have a grid of points where you compute the field. And then assuming you have a dipole, a vertical dipole, you're gonna compute the radiated power given the 1 watt power from an omnidirectional antenna, and you have the different received power levels here that you can see. So these are pretty low. Now in the bottom grid, remember how I have the or the bottom plot, how I have that access point where I put directional antennas in a circle, 8 of them. What I'm going to do for each point, this is already done in the SBR solve, but basically what I do is at each point, I compute the field per antenna, per each of those directional antennas, assuming all the other ones are turned off. And then I do that for each, and in post-processing, at each grid point, I will go over the different permutations for each of the field points of to sum all the fields, and then I'm going to choose and plot the one that gives me the highest power. So for each point you have so if it's 8 antennas, that's 255 possible different states or different combinations of those antennas, and based off that you compute the total field there based off the best selection that gives you the highest power. And that's what we plot in every part of this in this grid. And you can see obviously when you do this adaptive antenna selection process, you can see your received power is higher than the one when you just have an omnidirectional antenna. Maybe you don't notice as much of a difference where the access point is located in that small room, but further away you can see it makes quite a bit of a difference. The second study that we wanted to look at is the different how SNR changes with the transmit power. So obviously it's a bit of a trivial thing to plot, but it just to show how much the antenna selection process really plays a role. So for example, if for user 2, we can see for the omnidirectional antenna, it requires about, for the MCS, let's say the MCS 7 level, you save about, so this is maybe 18, and then we're here at 7. So let's say you save about 10 dBm of power by using this antenna selection process. In this antenna selection process, after you chose the optimal combination of the antennas, I did unit weights for each of the selected antennas. So that's how you get this orange curve. And then, but if I use the conjugate channel and maximal ratio transmission, you can see you get a further improvement and you save about 2 dBm of power. And then this is what I plot for each of the different users, the 3 users that I have. User 3 is a little further away from user 2, but it's actually, user 2 is located at a null, so that's why these 2 plots are relatively comparable. And then the maximal ratio transmission and the switch theme selection are on top of each other. And yeah, I would say, this is the workflow that we have. And again, just one more time, this is just a skill that we have built, and you just have to place your own antennas with your own HFSS designs, and you run this entire workflow autonomously and get the results, and just you get all of these kind of nice things that we have. One of the many workflows that we offer. Thank you.